Hi everybody, welcome to our first pre-lab video for Chem 211. This video is just the first of three, and I want to just give you a brief summary on what the entire dual unknown lab is all about. It's basically a lab where you are going to be assigned a partner, and you and your assigned partner will be assigned two unknowns. They are both unknowns that are pure organic liquids at room temperature. And it'll be you and your partner's goal to figure out from the information we supply to you what these two unknown compounds are from a list of possible compounds. Okay, so let's look at the three main pieces of data that you are going to be looking at to help you identify these unknowns and what these concepts represent. The first one will be acid-base properties. We're going to look at the acid-base properties of your unknowns and see if that can help us tell us something more about your unknowns. Then we're also going to look at the IR spectroscopy and the IR spectrum of each of your unknowns. IR is something slightly new to most of you. In our intro chem lab, we used visible spectra. Now we're going to go venture into the IR realm. It's kind of cool, as this cartoon, I think, illuminates. And last but not least, we're going to go venture with what Abby from NCAS calls, I think, her favorite instrument. It is called a mass spectrometer, and you will be getting a mass spectrum from this instrument. And this instrument and the mass spectrum's number one goal that'll help you with is it will give you the molecular weight of your unknown. Okay, so let's there'll be three videos, one on each of these ideas. So let's start with acid-base properties of your unknown, and how will those tests that you would have done, what information would they tell you about your unknown, and then we will supply you with that data to help you figure it out. Now, one of the things that you might have heard, and it might cause cold sweats from your intro chem, is pKa's, or those might be completely new to you. If a pKa is a completely new idea to you, please make sure to either ask me, Google it, find out what a pKa is. It is just an elaborate equilibrium constant that helps us understand the rules of acids, and it gives us kind of a sense of what's a good acid, what's a bad acid, pKa for acid. So here I'm hoping that maybe we can rely on some of your previous knowledge. For example, if I asked you if you wanted to stick your hand in a beaker of sulfuric acid or hydrochloric acid that was very concentrated, you would hopefully pause on that one and not do that, because you know those sound like very scary strong acids, and that's exactly what they are. So when you look over there on the left-hand side of the table, you can see there's HCl, H2SO4. These have pKa's that have negative values, like -8 equals the pKa for some of these acids, or -5. These are extremely strong acids and love to disassociate completely in water and give up H+, like it's going out of style. Here, take all my H+, please. I don't want any H+, have it all. And those are considered extremely strong acids. Organic chemistry will never have organic molecules that are generally as strong as our 7 strong acids. Okay, so let's take a look at the organic compounds that could be with your unknown, and more specifically the organic functional groups that are on this table that could be part of your unknown, and see if we can use that to help us figure out what your unknowns are. So the first thing I want you to notice is that the first major functional group that pops up closest to these strong acids is a carboxylic acid. It is the strongest organic acid that we know. And so we gave it the name. It'll be easy to remember. It's a carboxylic acid and has a pKa around 5. Okay. The next group of functional groups that you are going to play with is basically almost every other functional group that you're going to see in organic chemistry. They are essentially like water. They are harmless. They are neutral. They're not acidic. They're not basic. They will never pretend to be acidic or basic. And you need to hold on tightly to this, especially you can see alcohols. Alcohols look a lot like a carboxylic acid, but they also look a lot like water. So please keep alcohols and water in the same vein. They have pKa's around 16, and you don't mind sticking your hand in water or alcohols. Or drinking alcohol. Wait, no, sorry, maybe not now. Okay, so other functional groups that are neutral are ketones, aldehydes, nitriles, and amides. These are other ones that could be on your unknowns. So keep an eye out for them. They'll be boring. They won't show any acid-base properties. And then way out on the end here, I just want to highlight these amines, and those lone pairs sitting on those amines make them basic. You can see they're very poor acids. They hate giving up H+, but their pKb is a negative number. They love taking H+. So we will see amines acting basic in our dual unknown lab. And so these are the main functional groups that are part of your unknowns, and your unknowns must have at least one of these functional groups, okay? So when we do the solubility test, we start with water, and generally your liquid unknown is an organic liquid. You can even think of it as oil, and this would look like oil and vinegar in a test tube. Two layers that separate. One of these is water, one of these is your organic liquid, and they have no interest in dissolving in one another because, as you know, oils are very big organic molecules and very nonpolar. And therefore they do not have the same polarity as water and don't want anything to do with water. So they create their very own layer. Most of your organic unknowns will have this. As you can see, a lot of functional groups are going to behave just like this oil and vinegar kind of idea of a separate heterogeneous solution. But if we took, say, your unknown and it had an organic acid like a carboxylic acid on it and mixed it with some dilute NaOH, some base, then they would mix. And if we took HCl, a dilute aqueous HCl solution that's acidic, and mixed it with an amine, they would mix. Now, does that mean these organic compounds all of a sudden just love the acid-base properties of the solutions you put them in and nothing's happened to them? They've just all of a sudden decided to become polar and love water? No. Let's be really clear. When you add NaOH, for example, to your carboxylic acid, you are doing a chemical reaction on your carboxylic acid that hated water to begin with. But now that NaOH has deprotonated your carboxylic acid and turned it into a salt, a charged species, an ionic compound. And as you know, salts love water. So all of a sudden your organic unknown has become charged and can't wait to just go swim in all that 95% water that's in that aqueous basic solution and generate this homogeneous solution. Okay, so keep that in mind when you're doing acid-base solubility tests. You're actually doing chemical reactions. So the same thing will happen if I took 5% HCl and added it to an amine. Notice that lone pair is going to be in love with the H+, but once it does, it becomes positively charged. It becomes ionic, and let's dissolve in some water because I'm charged. Woohoo! It doesn't even matter how big the R group is, the rest of the molecule. I think that's why they use R. That makes sense, huh? Rest of the molecule, R. I'm not sure, but it's a very common nomenclature for the rest of the molecule. Would dissolve with the amine and just go swimming in that aqueous acidic solution. So solubility tests will be very helpful to us if we have a carboxylic acid on our unknown or if we have an amine on our unknown. If we just have a neutral compound, Not very helpful. Notice it still leaves a lot of functional groups that are possible for your unknown. Okay. Oh, what? Warning, warning. Well, you could get this weird false positive, sort of, in all of your solubility tests with these acid-base solutions. You could get your unknown to love to dissolve in water, 5% NaOH, and 5% HCl. It could love every solution. Now, that means one of two things. That means your unknown compound has both an amine and a carboxylic acid on it. And we've given you the two different functional groups on some of your molecule somewhere, like an amino acid. I'm here to tell you right now, we have not done that. Nobody has amino acids. Nobody has amines and carboxylic acids on the same structure. Okay? What you have in this situation is a compound that's organic, but all of a sudden loves to dissolve in pure water? Wait a second. How can an organic compound dissolve in pure water? Well, it's tiny. So organic molecules that are only 5 or 6 carbons in size, they are not very nonpolar, especially if you stick one of these functional groups like an alcohol on it, an OH or an amide, something that has some electronegativity to it, and create partial charge. And now it's small and it's got a little charge, and all of a sudden the water comes in and it's like, okay, I like water. I'm small. I'll go swim in the water. And it swims in all of the water, every single aqueous solution. So it will also swim in the 5% NaOH because it's 95% water. It'll swim in the 5% HCl, not because it's basic, but because that's 95% water. So be on the lookout for unknowns that love to dissolve in everybody. If they dissolve in everybody, then they are small. And you might get one more piece of information. If I took the pH test of pure water with my dissolved unknown, maybe when my unknown dissolves, a little teeny amino acid, a little teeny carboxylic acid, or a little teeny amine, maybe it changes the pH of pure water. And that could be a clue as well. So be on the lookout for pH changes of pure water. Okay? In the end, ask yourself, why don't we do the pH test then of the 5% HCl and the 5% NaOH? That's a results question, post-lab question. Feel free to ask me as we do the lab coming up. And now, practice. Practice, practice, practice. That's what Orgo is all about. The more you can practice, the easier this foreign language known as Orgo in Orgoland will be for you. So here are a couple practice problems. Please pause the video, try these, and then unpause the video when you want to see the answers. I'll show them to you in just a second. Okay, here come the answers to these two questions. Hopefully you got them, and if not, please feel free to email me and let me know. In the first question, the compound is insoluble in water, but it's hard to tell. You might have some mixing lines, something that's not quite sure. So we're going to test the pH of the water anyway, and lo and behold, it has a pH of 10. My unknown is basic. I could stop right there and just say I have an amine, but being a very thorough Wellesley student, I continued to do the test, and in lab I didn't have 5% HCl, I had 3 molar HCl. So it's still a dilute HCl solution. This will happen. Please don't freak out about it. These are aqueous dilute solutions that are acidic, and it did dissolve this unknown, and therefore the most likely functional group that I have at least is an amine. I have no idea. It might have other functional groups. You could also have some ketone or alcohol somewhere else on this molecule, but due to this test, the only thing I can tell you is it has an amine. And I just want to remind us that all of these solubility tests are actually reactions taking place. So please get very comfortable with writing the actual deprotonation of the acid or protonation of the base. And therefore, you're going to have to be able to spy your functional groups. You need to know what a carboxylic acid looks like and what an amine looks like. Those are our acid-base functional groups. So I put lots of functional groups on these molecules to try to trip you up. Did you spy the only carboxylic acid on the first molecule? And hopefully you didn't fall for the alcohol that I put in there as an OH, which is neutral and has no interest at all in getting deprotonated. The only thing that'll deprotonate is the carboxylic acid. And on the bottom one, the last question, I threw in another little curveball. There is an amine that got protonated by the HCl. But notice the other nitrogen looks like an amine, but it's not. Yep, it's an amide. You stick a C double bond O next to a nitrogen, put those two next to each other, and you've created a whole new functional group that is no longer basic. The lone pair on that nitrogen has a little interest in doing something called resonance. Ooh, cold sweats, yes. See if you can draw the resonance structure for that amide, and you will know why that amide's lone pair does not want to get protonated by H+. It's too busy leaving and doing resonance. Hard to protonate something that's not there. Cool ideas. Keep coming up with your questions, and I hope to see you in office hours soon. Definitely see you in lab soon. Bye.